According to the National Electrical Code, specifically Section 110.14 Current A, the ampacity of a conductor must be sufficient to carry the maximum load without exceeding its ampacity in an ambient temperature of 40 degrees Celsius, which is 104 degrees Fahrenheit, unless otherwise specified. This means you need to ensure the wire size you select can handle the current demanded by the circuit at its expected operating temperature. Consider a scenario with a 60 amp breaker and number 6 THHN wire and conduit. Number 6 THHN wire has an ampacity of 55 amps at 40 degrees Celsius. Because the breaker is rated for 60 amps and the wire is only rated for 55 amps, this combination is not suitable. The breaker's rating exceeds the wire's ampacity, potentially leading to overheating and a fire hazard if the circuit were to draw more than 55 amps. Now, let's examine National Electrical Code Section 240.4b. This section addresses the protection of conductors. Specifically, 240.4b allows you to use 60 degrees Celsius terminations with 75 degrees Celsius conductors, provided the ampacity of the conductor is not reduced below the termination temperature rating. This means if you're using a wire rated for 75 degrees Celsius, like THHN, but connecting it to a device with 60 degrees Celsius terminals, you must use the ampacity column for 60 degrees Celsius when determining the allowable current. In our scenario, the number 6 THHN conductor is rated for 75 degrees Celsius. While the 60 degrees Celsius terminations are acceptable under 240.4b, it is crucial to ensure that the conductor's ampacity matches or exceeds the breaker's rating at the termination temperature. Again, since number 6 THHN is only rated for 55 amps at 60 degrees Celsius, this application is not acceptable. The overriding principle is that the conductor must be protected against overcurrent. The overcurrent protection device, in this case, the breaker, should be sized to protect the conductor, not the load. This means the breaker's rating should not exceed the conductor's ampacity. In general, conductors are chosen to have an ampacity equal to or greater than the non-continuous load plus 125% of the continuous load. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. If the breaker is larger than the conductor ampacity, the conductor is not properly protected. To correctly apply these rules, you need to know several key factors. Firstly, you need to know the ambient temperature in the area where the conductors will be installed. Higher ambient temperatures reduce the ampacity of conductors. Secondly, you need to know the temperature rating of the terminations on the equipment. Terminations are typically rated for 60 degrees Celsius or 75 degrees Celsius. Thirdly, you need to know the type of conductor being used, such as THHN, THWN, or XHHW, as each type has a different ampacity rating. Fourthly, you need to know if any dirting factors apply. Dirting factors are used to reduce the ampacity of conductors when multiple current-carrying conductors are installed in the same conduit or cable, or when the ambient temperature is higher than the rating of the conductor. The National Electrical Code provides tables to determine the ampacity of conductors under various conditions. For example, Table 310.15b16 in the 2017 NEC, which is Table 310.16 in later editions. These tables list the ampacity of different types of conductors based on their size and temperature rating. It is important to consult these tables and apply any necessary correction or adjustment factors to determine the allowable ampacity of the conductor in a specific installation. In our example, the initial problem specified is INSCO breaker. It's crucial to ensure the equipment used is properly listed and in good working order. INSCO breakers have a history of issues, and their reliability should be verified or alternative, more reliable breakers considered. In the given scenario, connecting a 2-pole 60 amp INSCO breaker with 60 degrees Celsius terminations only to number 6 THHN and conduit for a feeder to a sub-panel is not acceptable. The ampacity of the conductor must be equal to or greater than the rating of the breaker. Since the number 6 THHN conductor has an ampacity of only 55 amps at 60 degrees Celsius, it is insufficient for use with a 60 amp breaker. You would need to use a larger conductor, such as number 4 THHN, which has an ampacity of 70 amps at 60 degrees Celsius, or reduce the breaker size to 50 amps. It's also important to consider the voltage drop in the conductors. Voltage drop occurs when the voltage of the load is lower than the voltage of the source due to the resistance of the conductors. The National Electrical Code recommends limiting the voltage drop to 3% for feeders and 5% for branch circuits. Voltage drop can be calculated using the following formula: voltage drop equals 2 times K times I times D divided by circular mils, where K is the direct current resistance for the conductor material, which is typically 12.9 ohms for copper, I is the current in amps, D is the one-way distance of the circuit in feet, and circular mils is the cross-sectional area of the conductor. If the voltage drop is excessive, it may be necessary to increase the size of the conductors. Always consult the latest edition of the National Electrical Code and follow all applicable local codes and regulations when installing electrical wiring. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself from electrical shock. It is always recommended to hire a qualified electrician to perform electrical work. They have the knowledge, skills, and experience to ensure the work is done safely and in accordance with all applicable codes and regulations. Remember that this discussion is for educational purposes only and does not constitute professional electrical advice. Always consult with a qualified electrician before making any electrical installations or modifications. Failing to follow these guidelines can lead to dangerous situations, including electrical shock, fire hazards, and equipment damage. Let's look at some additional considerations regarding conductor ampacity and breaker sizing. Firstly, the National Electrical Code allows for specific exceptions under 240.4D for fixture wires and flexible cords. These conductors have specific ampacity limitations based on their construction and intended use. These exceptions are specifically outlined in tables within the National Electrical Code, and you should consult these tables directly when working with fixture wires or flexible cords. Secondly, when dealing with motor circuits, the overcurrent protection requirements are different than those for general-purpose circuits. Motor circuits typically require both overload protection and short-circuit protection. Overload protection is designed to protect the motor from overheating due to excessive current draw, while short-circuit protection is designed to protect the circuit from damage in the event of a short circuit. The National Electrical Code provides specific rules for sizing the overcurrent protection devices for motor circuits, taking into account the motor's horsepower rating, voltage, and full load current. Thirdly, when installing conductors in underground conduits, the ampacity of the conductors may be affected by the soil conditions and the depth of the burial. The National Electrical Code provides guidance on how to adjust the ampacity of conductors in underground installations based on these factors. Fourthly, when conductors pass through different temperature zones, the lowest temperature rating of any part of the run determines the overall ampacity of the circuit. For example, if a conductor runs through a hot attic and then into a cooler wall cavity, the ampacity of the conductor must be based on the temperature rating of the attic section. Fifthly, consider the impact of harmonics on conductor ampacity. In circuits with significant harmonic content, such as those serving non-linear loads like electronic equipment, the neutral conductor may carry a significant amount of current. The National Electrical Code requires that the neutral conductor be sized appropriately to carry the expected harmonic current. In some cases, it may be necessary to upsize the neutral conductor to prevent overheating. Sixthly, when using parallel conductors, all conductors must be the same size, material, and insulation type. They also must be terminated in the same manner. The overcurrent protection device must be sized to protect the smallest conductor in the parallel set. Seventhly, keep in mind that the National Electrical Code is a minimum standard. In some cases, it may be desirable to exceed the minimum requirements to improve the reliability and performance of the electrical system. For example, you might choose to upsize conductors to reduce voltage drop or to provide extra capacity for future loads. Eighthly, always document your work clearly and accurately. This includes labeling all circuits and panels, as well as providing a written record of all calculations and decisions made during the installation. Accurate documentation will make it easier to maintain and troubleshoot the electrical system in the future. Ninthly, remember that electrical codes and standards are constantly evolving. It is important to stay up to date on the latest changes to the National Electrical Code and other applicable codes and standards. You can do this by attending training courses, reading industry publications, and consulting with qualified experts. Lastly, if you're ever unsure about any aspect of an electrical installation, it is always best to consult with a qualified electrician. They can provide expert guidance and ensure that the work is done safely and in accordance with all applicable codes and regulations. Understanding and applying these principles helps ensure a safe and reliable electrical installation.